Hello everyone, this is Firoz Nada. In this video, we will see introduction to a design of column. We will see what are the terms that are used in the design of column. So basically, you have two types of column. One is short column and other is long column. And again, the short column is divided into different categories based on uh, based on the application of the load. So we have axially loaded column, then we have uniaxial bending, means bending will be there in one direction, and you have biaxial bending will be there in both the direction, in x direction as well as in the y direction. So first we have to see how to identify whether a column is a short column or a long column. Okay, so we have to decide whether the column is a short column. In the exam, sometimes they will give you design a short column, but at times they will not give you what is the column, whether the column is a short column or a long column. In that case, you have to decide what column you have to design, whether it's a short column or it's a long column. Okay, so it is decided based on the ratio of effective length of the column divided by least lateral dimension. If this ratio is less than 12, then we say that the column is a short column. If it is greater than 12, then we say that the column is a long column. So L effective is effective length of the column, and we have to find effective length of the column based on the end condition. D minimum is the least lateral dimensions of the column. If this is the size of the column, you see 450 mm by 400 mm. Here 400 mm is the least lateral dimension of the column. Okay. Now you see effective length, it depends on two points. It depends on two criterias. First is it depends on support condition of the column. What is the support condition of the column? Whether the column is a fixed column or it is a hinge column, whatever the support condition is there, depending on that, you have to find effective length of the column. It also depends on unsupported length. So how to take unsupported length? It is given in IS code 456 2000, page number 42, clause number 25.1.3. So based on that, we have to decide what is the unsupported length in our building. Okay, so you see, we have a different types of building. For different types of building, IS code has given different unsupported length. So in case of slab and beam construction, normally this is the building that we encounter, slab and beam construction. So in that case, in this case, the unsupported length is a clear distance from the floor to the underside of the shallower beam. So if you see, if you have two beam, one is the primary beam and other is the secondary beam. Secondary beam is the shallower beam. Okay, so the unsupported length is the distance from the floor to the bottom of the shallower beam. So this is in the, from this figure, the unsupported length is very much clear to you. We have to determine effective length of the column from IS 456 2000 from annexure E. The title of this annexure is effective length of the column. In this annexure, we have one table, table number 28, and we will get the value of effective length of the column from table number 28. To determine effective length of the column, we must know the end condition of the column. So effective length of the column depends on the end condition of the column. In the strength of material, you have studied that uh, depending on the end condition of the column, we can determine effective length of the column. Say end condition, it could be both the ends are fixed, one end is hinged, other end is fixed. Okay, so in that way we have studied, but here they have not given with respect to the support. What they have given with respect to the position and with respect to the rotation. So case number one, you see, number one, what they say, effectively held in position and restrained against rotation in both the ends. Effectively held in position means, what is the meaning of this? The end is not allowed to move in the horizontal direction, and it is also not allowed to move in the vertical direction. It is effectively held in position. Okay, second point is restrained against rotation. Both the ends are not allowed to rotate. So this is the only case with the fixed support. In the fixed support, the end is not allowed to move in the horizontal as well as in the vertical direction, and also the ends are not allowed to rotate. Okay, so here both the ends are fixed. When this condition is there, then effective length of the column equal to 0.65 L, where L is unsupported length. Case number 2, you see, effectively held in position at both the ends. Both the ends are not allowed to move in the horizontal direction as well as in the vertical direction. They do not have horizontal and vertical deflection, but what they say, restrained against rotation at one end. So what we can understand, one end is allowed to rotate but other end is not allowed to rotate. Okay, so here we can understand that one end is having hinge support and other end is having fixed support. In the fixed support, the end is not allowed to move in the horizontal as well as in the vertical direction, and also it is not allowed to rotate. But in case of hinge support, the end is allowed to rotate but it is not allowed to move in the horizontal as well as in the vertical direction. So in the same way, you have to see the end condition of all these cases and then you have to determine effective length of the column. Case number 3, you see, effectively held in position at both the ends but not restrained against rotation. See, both the ends are allowed to rotate but they are not allowed to move in the horizontal as well as in the vertical direction. And what they say, effectively held in position but not restrained against rotation. You do have some rotation at both the end. Here both the ends are hinge support. So in this case, effective length of the column equal to 1 into L, where L is unsupported length of the column. So a short column is subjected to 3 kinds of load. So depending on that, we have to design different short column. We have to design for axially loaded column, uniaxial bending and biaxial bending. So depending upon the position of the load on the column, we have 3 different short columns. Okay, so depending on that, depending on the position of the load, we have to design 3 different columns. Axially loaded short column, it fails due to compression only. It fails due to crushing only if it is about to fail. There is no bending in the axially loaded column, whereas uniaxial and biaxial column, it fails if it is about to fail, it will fail due to bending only. Okay. Now the bigger question is how to identify whether the short column is the axially loaded column or it's a uniaxial or biaxial. How to identify it? See, identification of it depends, it largely depends on the position of the column in the structure. Okay, so based on the position of the column in the structure, we can easily decide whether it is axially loaded, uniaxial and biaxial. So based on the position of column, we can, so this is the size of the building that we have and we have to show the position of the column. So these are the possible position of the column in the structure and it is connected through beams. So all the columns are connected through the beams and the load is transmitted from the beam to the column in terms of bending moment and reaction. Okay, so load is transferred to the column. It is transferred to the column. In the analysis, you have learned that it is transferred to the column in terms of bending moment and the reaction. Now you see, I have numbered the columns. Let's talk about column number 5. You have bending moment in the left direction. You also have bending moment in the right direction. So if the bending moments are equal in the x direction, so these bending moment are equal and opposite. So the net bending moment in the x direction is 0. Similarly, if you have bending moment above column and below column and they are equal and opposite, so the net bending moment in column 5 in the x direction as well as in the y direction is 0. So there is no bending moment created in column 5. So column 5 is nothing but it's a axially loaded column. The bending moment gets balanced from either side. Now you consider column number 2. In column number 2, you have bending moment from the top, you have bending moment from the bottom. So these bending moments are equal and opposite. So the bending moments cancelled in the y direction, but in the x direction you have bending moment from the right direction and this bending moment is not cancelled. Okay, so there is one bending moment, which is not nullified. That bending moment is in the x direction. So this column the moment from one side is not balanced. So column number 2 is uniaxial bending. So there is a moment in one direction. Okay, the another moment, the moment in the another direction is nullified. It is cancelled. It is balanced. But the moment in x direction is not balanced. So column number 2 is uniaxial bending column. Okay. Now you see, you consider column number 1. So bending moment from either side, bending moment from x side, x direction, and bending moment from y direction is not balanced. So you have two bending moment from either side is not balanced. So column number 1 is biaxial bending. Now we will see design of a axially loaded short column. So first we have to understand what is a axially loaded column. The literal meaning of the axially loaded column is that the load is acting at the center. If this is the size of the column, the cross section of the column, and at this point at the center of the column, the load is acting. Okay. However, IS code 456 2000 has a different definition. What they say in clause number 25.4, page number 42, what they say, all the columns irrespective of the types of column, whether short column, long column, in short column axially, uniaxial or biaxial, so all the columns shall be designed for minimum eccentricity. What they say, there is some minimum eccentricity in all the columns, and we will consider when we design the columns, we will consider the minimum eccentricity. Okay. Now what is minimum eccentricity? They have given in the same clause, they have given two values, uh, equal to L by 500 plus D by 30 or 20 mm, whichever is smaller. So whichever smaller value you will get, that will be the minimum eccentricity. And what is L? L is the unsupported length of the column, and D is least lateral dimension. Now you see, they say that we have to consider minimum eccentricity. Okay. Now what is the axially loaded column? How to define the axially loaded column in this case? Okay. So the axially loaded column are those columns wherein the eccentricity, the value of E is between minimum and maximum. We have seen what is the minimum value. Okay. And what is the maximum? It is also given in IS 456. The maximum value is 0.05 into least lateral dimension into D. Okay. It is given in clause number 39.3, page number 71 of IS 456 2000. Okay. Now we also have to understand what is eccentricity. Okay. It's a distance of the load from the center of the column. If this is the center of the column, y axis, x axis, then this is the point. So at this point, okay, this is the perimeter of the maximum eccentricity. If the load is acting inside this perimeter, then we can say that it is the axially loaded column. We already have defined what is axially loaded column. It is a eccentricity. If the eccentricity lies between E minimum and E maximum, then that column is axially loaded column, and this perimeter defines the maximum eccentricity. And beyond this perimeter, if the load is acting beyond this perimeter, then that column will be uniaxial column or biaxial column. We will see how the uniaxial and biaxial columns are defined based on eccentricity. Okay. Now you see, if the load is acting at this point, okay, it has eccentricity with respect to y axis, and there is no eccentricity with respect to x axis. So what we can understand, the y axis is bending, but x axis is not bending, because eccentricity is not with respect to x axis, eccentricity is with respect to y axis. Okay. So this is the case of uniaxial bending. Okay. So there is the bending moment with respect to y axis and no bending moment with respect to x axis. It is the case of uniaxial bending. Okay. So if this is the point of application of the load, it has eccentricity with respect to x axis as well as with respect to y axis, and it is a case of, it will create bending moment in both the axis, y axis as well as x axis, and this is the case of biaxial bending. With regards to design of a axially loaded short column, IS 456 2000 has given one formula. They have given one formula which is about the load carrying capacity of the column in clause number 39.3, page number 71, IS 456-2000. What is that formula? That formula is PU equal to 0.4 FCK AC plus 0.67 FY-ASC, where AC is area of the concrete in column and ASC is area of steel in column. Now this formula has been derived based on the load carrying capacity of the concrete and steel. In column, we have the steel as well as concrete. So this formula has been derived based on the load carrying capacity of the concrete and steel. So what is the load carrying capacity of the concrete? Equal to FCK AC, and the load carrying capacity of steel is FSC into ASC. FCK and FSC are the stresses in the concrete and steel corresponding to maximum strain in compression. So what is the maximum strain in compression? Maximum strain in compression is given in IS code in clause number 39.1. They say that the maximum strain in compression in axially loaded column is 0.002. So based on these values, the formula has been derived. It is given in IS 456-2000. Directly you can take this formula. Okay, now we can modify this formula based on our criteria. You see, AC is area of concrete excluding steel, and AG we can take total area which is including concrete and steel. AC equal to AG minus ASC. We can substitute AC, the value of AC in terms of AG and ASC, and we can modify this formula. Now you see, this formula can be used. It is a load carrying capacity of axially loaded short column. It can be used for analysis and also for the design. In analysis, what will be given to you? The design will be given to you. The area of the column will be given to you, the steel in the column will be given to you, and you will be asked to find the load carrying capacity of the column. Okay, in case of, you see, in case of design problem, the load will be given to you. What load is coming on the column will be given to you, and you will be asked to design to decide the cross section of the column, and you will be asked to calculate the reinforcement and provide the reinforcement in that particular column. Okay, so we have two types of problem: analysis problem and the design problem, and we can use this formula to do analysis as well as design. Now you see, this formula can only be used when the column is a short column and as well as it is axially loaded column. You have to ensure that whatever column you are dealing with, it should be short column as well as it should be axially loaded column when you are using this formula. This formula is not applicable for uniaxial and biaxial bending column. Okay, so how to ensure that? We know how to decide the short column. L effective by D minimum, least lateral dimension should be less than 12. And how to decide the axially loaded column? E should be between E minimum and E maximum, we have seen that, and from that we can say that the least lateral dimension should be E more than equal to 400, and it should be more than 0.12 L. If this case is satisfied, if the least lateral dimension is more than equal to 400 mm, if the least lateral dimension is more than 0.12 L, where L is unsupported length, we can say that the column is axially loaded column. Then we can use this formula. Thank you very much for watching this video. I hope that you enjoyed it. This is about the introduction to the design of column, and in the next video will be about the design problem, the analysis problem.